The last video focused on how to amortize discounts on bonds payable using something called the straight line method. In this video, we're going to be doing the same sort of thing, except using a different method. We'll be amortizing using something known as the effective method. The effective method is used because it provides better matching. Recall that matching is the idea, the principle of matching our expenses to the revenues they help earn in the period the revenues are earned. Let's take a look. First, I'd like us to refamiliarize ourselves with the example from the prior video, 15-3. In that example, we dealt with bonds that had a maturity value of 1 million, a stated rate of 4%, making for a stated semi-annual rate of 2%. It was a 5-year semi-annual bond, which made for 10 semi-annual periods, and the bond price was $980,000. So this was the amortization table that's highlighted here that we did in the prior video. We can see that the interest payment was a fixed $20,000 every period. The discount balance started off at $20,000 and was evenly allocated to each and every period thereafter. In other words, a straight line amortization was used. That means that the interest expense was a fixed amount each and every period. The discount balance went down to zero. The bond carrying balance began at $980,000, and by the end of the life of the bond, we had worked our way back to the maturity value. What I've added is an additional column. That additional column looks at interest expense divided by the bond carrying balance. Allow me to explain. From the issuance of the bond carrying balance is $980,000, and it is that way for the next 6 months until the first payment. For that period of time, we recognize an interest expense of $22,000. If we take $22,000 and divide it by $980,000, in other words, this $22,000 here, if we take $22,000 and divide it by $980,000, we get 2.2449%. We can do the same thing in the next period. We can take $22,000 and divide it by the preceding carrying value on the table of 982, and now we get a different percentage. And the point I'm trying to make is that the interest expense as a percentage of the carrying value is changing each and every period. Now we have to think about if that is good matching or not. What was that rate that was in effect at the time the bond was issued? That is effectively the rate of interest that the issuer is paying. How do we reflect that rate of interest in our interest expense? That's what the effective method does. Let's take a look. This is example 15-4, and we have a bit more information. Assume that there are $1 million of 4% 5-year semi-annual bonds issued on Jan 1st, when the market rate is quite specific, 4.4506%. We are going to create an amortization table and then record journal entries for the first year. So what is the maturity value here? It is $1 million. The stated rate is 4%, which makes for a semi-annual rate of 2%. The market rate that's in effect at the time is 4.4506%, which makes for a semi-annual rate of 2.2253%. The number of periods, 5 years, semi-annual is 10 periods. The payment is $1 million multiplied by the semi-annual rate of interest, the stated semi-annual rate, and the bond price is going to be equal to something called the present value. We are taking the present value of two components: the present value of the annuity, that is the regular periodic stream of interest payments that has an end date, and the one lump sum maturity value. Both of those are taken together. Their present value can be worked out with a BA2 Plus calculator. I'm using Google Sheets, so I'll just show you how to do it with Google Sheets. The present value involves taking the market rate of interest that's used for each period, so the semi-annual market rate of interest. Then we take the number of periods, which is 10, and then we take the payment amount. The payment amount is $20,000. You might notice that I've used a negative sign there, and that's because the payment is a cash outflow. Then finally, we have the future value. I'll use a negative amount there as well to indicate that that $1 million, the lump sum, is an outflow that's paid out at the end. We can see that the present value is just about $980,000. So for the sake of consistency with the previous example, I'll make it $980,000. Our bond carrying balance is going to equal the present value, or the bond price. The discount balance is still going to be $1 million subtract the carrying balance. Next, we can fill in the interest payment column. We know that if we took $1 million and multiply that by the semi-annual rate that's stated in the contract of 2%, we would get $20,000, and we could use that all the way through. Where things start to change is here with interest expense. Recall that when we are dealing with the discount, the interest expense is equal to the cash that is paid, the interest payment, plus the amount of discount that is allocated to the period. What we are trying to do here is allocate just the right amount of discount so that the interest expense is a consistent percentage. We know that the interest expense that gave rise to the discount is the market rate of interest. 4.4506% was different from the stated rate at the time. Semi-annually, the market rate of interest is 2.2253%. We're going to use that rate in our calculations. We can take the semi-annual rate that was in effect at the time the bond was issued and multiply that by the preceding carrying value. Here we get $21,808. The difference then between the interest expense and the amount paid must be the amount of interest that was coming from the discount. The remaining discount balance is the original balance subtract what was allocated to the period, or in this case, $18,192. If we were to take the maturity value and subtract the discount balance, we would have our new carrying balance. We can carry this all the way through and see what things look like. So that almost worked out perfectly. In fact, the reason we're off by $1 is because I had set the present value to $980,000. If I was to remove that, you would see everything would work out perfectly. The only reason I added the $1 is I wanted to make one point clear. I wanted you to be able to compare this example, 15-4, perfectly to 15-3. If we were to take the interest expense from the first period, $21,808, and divide it by the preceding carrying value, we would see a couple of things. The first thing we would see is that the rate of interest matches the market rate that was in effect perfectly. The next thing that we'll see is that it is consistent all the way over the life of the bond. And that differs from what we saw before. If we go back up to 15-3, you'll see that the interest as a percentage changed over the life of the bond. However, the interest expense amount remained the same. The interest expense as a dollar amount changes when we use the effective method. But as a percentage, it remains consistent. So this makes for better matching. Now we can go on to do some of the journal entries. So the first journal entry is going to be similar to 15-3. When we debited cash for $980,000, we debit discount payable for $20,000, and we credit bonds payable for $1 million. On the first payment date, we should be able to get our numbers right from the table. Cash is $20,000, the interest expense is $21,808, and so the amount of discount that's amortized is $18,08. Debit interest expense $21,808, credit discount on bonds payable for $18,08, and credit cash for $20,000. Finally, at the end of 20x1, once again, we can take those amounts straight off the table. and we get a debit to interest expense of $21,848, a discount on bonds payable of $1848, and a credit to cash of $20,000. So a lot of people find this method of amortization, the effective method, to be a lot more difficult than the straight line method. And frankly, it is more complicated. So I recommend downloading the spreadsheet and trying it out yourself several times until you get the hang of it.